I'm Sriraam, Sriraam Natarajan. I've been a faculty here for a little over 2 years. I work in machine learning. This is our group. Kind of an outdated photo. I think we have to take one before the holidays. So we are in 2015, but the problems from 2005 still persist. We couldn't get my laptop to communicate with the projector. I couldn't get my printer printing in the morning. So it's been an interesting day so far. So this fiasco is kind of in line with that. Okay, so if there is some formatting issues, please understand, again, this is due to creating the PowerPoint in my laptop, but using it in the school computer, which seems to be from 1850, I think. That's how old it is. Anyway, so I'm Sriraam. I'm going to talk about human-in-the-loop statistical relational learning. As always, I'm taking credit for my students' work. Most of these are PhD students, particularly Tushar, Philip, Shu, and Raksha. I'm presenting their work here, but the others have been deeply involved with this research as well. Again, thanks to my collaborators who are on this work. It's kind of spanning, actually spanning like 2-3 continents, a few schools across the US. And always a thanks to the funding agencies who keep us afloat. So what I'm hoping would be the key takeaway from this message is, from this talk, is that we are interested in learning from structured noisy data. I'll explain what structured noisy data is, but you can think of any data that's in a relational database that has probably noise and uncertainty around it. Okay, so that's what I'm calling as structured noisy data. We use probabilistic logic, also called as statistical relational learning, for learning. The key idea in this talk is to learn multiple weak classifiers and somehow combine them. The idea is kind of letting 1,000 flowers bloom, and combining them might be very useful. So we are showing that this is extremely efficient, which is what I'm hoping to convince at the end of the day. The second part of the talk, which we are really excited, is learning with human in the loop. So when I started my faculty position, which was in 2010, they said, figure out a problem that you could solve in 6 years, and that has your name on it. So I decided to address the problem, really challenging task of model learning in relational probabilistic data. Okay, and so that was my first part. And then Pedja came up and said about a year and a half back, okay, Sriraam, now you're nearly at the end of your assistant professorship. You should start thinking about what next for the next 5 years. So what I'm trying to do is figuring out how to bring human in the loop. So first is only data. The next is bringing human in the loop. And I'm hoping that by the end of the talk, I can convince you that we are looking at multiple types of human interaction. Okay, so just a primer. This is an AI or intelligent systems seminar, so you all know what machine learning is. We have a bunch of points or examples, a bunch of features or attributes that describe these examples. The goal is to fit a classifier. This is the simplest classifier. It's a linear classifier. This was back in the 1940s, and we have really improved. We have nonlinear classifiers now, so we've improved the representation of these classifiers. And more importantly, we have scaled them up. We can handle a lot of features. Again, this slide is from 1850. So we can handle a lot of features. We can do dimensionality reduction, project them to different spaces as we please, project them down, project them up, do whatever crazy thing we want. We are in the age of big data, which means that we can handle lots and lots of examples as well. Okay, so we know this. There's nothing new here. But the thing is that most of these data are in terms of a matrix or a vector. So we assume that most data can be interpreted or represented as a vector, and then we plug in our favorite learning algorithm on top of these vectors. Okay, it works. It works for many cases. Okay, and some of you, if you are a computer science student or a computer science faculty, should probably remember Jennifer Neville from Purdue came and gave an excellent talk 1 year back, and her thesis was actually showing that if your data is multi-relational, you taking a multi-relational data and projecting them onto a single table loses autocorrelation information and linkage information. More precisely, let's look at an example like this, where we are looking at an electronic health record. Here you have patients interacting with physicians, and physicians are looking at some symptoms. They could prescribe lab tests, they could prescribe prescriptions, they could prescribe further diagnosis, and so on and so forth. And if you look at it, there is not this, I mean, these electronic health records don't have the same amount of information for each of us, okay? So for instance, last 2 weeks I've been to the hospital 4 times, okay? And Rahul looks extremely healthy, so he's probably going to the hospital once in 4 years. We don't have the same amount of data. If you start projecting all of us to the same feature space, you're going to lose some information, okay? So this is from the medical record space. You can think of this in the social network space. Let's say I want to predict how popular somebody is by looking at the friends in Facebook, okay? Most of us are kind of losers. We are professors. We don't have more than 250, 300 friends. But then I talk to these people, and my student who's not yet 25 tells me that he or she has 800 friends. I'm like, what? So the point is that if I'm going to look at the attributes of friends to predict how popular I am, it's almost impossible to project all of us onto the same feature space. That's the idea, okay? So what I'm trying to say is that these rich representations should be handled as they are. The other thing is electronic health records particularly are full of noise, okay? So this is actually a snippet that we got. So if you look at the blood glucose, it's between just in a week, apparently the glucose level went up from 42 to 450. If this is a true data point, we probably will not have one more entry for this patient, because such a jump would probably cause a heart attack, okay? As funny as it sounds, it is actually the case in many electronic health records. And most of the data is missing, and so on and so forth. So there's noise in the data is multi-relational, it can be uncertain, you don't really know what to put. You know, so today morning I think I don't know, I flexed my knee, I went to this doctor, he took a bunch of x-rays, and he says, your x-rays look fine, but clearly something is wrong, and I'm not able to say what it is. So let's try one thing, and if it doesn't work, we'll go for an MRI, okay? So the point is that what he has said is extremely uncertain, okay? And we need to be able to learn from this kind of uncertain data. That's the goal of my lab, okay? And another example is nice from this text runner. I don't know how many of you use text runner. It's a beautiful tool which kind of became now the AI tool, Allen Institute of AI, okay? So that kind of this tool merged into that company. So if you look at text runner, which is a natural language semantic search engine, you have things like paper discussing a topic, maybe I can't even read the number, 65 times, covers the topic 54 times, and so on and so forth. So you have object, which is a paper, another object, which is the topic, and multiple relations. Paper could discuss a topic, paper could cover a topic, paper could talk about a topic, paper could address a topic, present a topic, provide a topic, right? And what we are trying to do is we are trying to quantify how much of these relations are true, okay? So the other way to say is you have a graph, you're looking at who is a friend of whom, who co-authors with whom, right? Such data are naturally inherently relational, and we are interested in learning from these relations, okay? So, and the point is, as my lab and my experiments will show, this kind of data, complex structured data and uncertain data, noisy data occurs everywhere, from planning to games, where we had some results with real-time strategy games. People who work in NLP have been frustrated with this for a long time. Robotics, George Konidaris, for instance, last week talked about the same problems, where they are having the same problems. He stopped with doing just one domain, one agent acting in one world. If I change the world, the representation breaks. We kind of agreed on that. So we need some richer representation, okay? And it's there everywhere, we know that. So, and many of you who are classic AIers are thinking, why is this guy harping about representation? We know this. And the answer is yes, we know this. We have addressed each of them separately. We have addressed small combinations of them. So we have done learning, decision trees, optimization, support vector machines. Sorry, this slide was prepared 4 years back, so I don't have deep belief networks on it, but you get the gist. Logic, again, is a rich tool for representing structured information. We have been using that for a long time. We know how to perform inference in these structured representations. Efficient algorithms exist. It's a research that's been going on for, I don't know, centuries. Similarly with probability, starting with the days of Thomas Bayes to more recently Markov, Kolmogorov, there's so much work done on probability theory, and that's there. And we have started putting them together. We have logic and learning. There's a nice field called inductive logic programming, which actually induces Horn clauses from data. So you can just run these algorithms. They induce if-then-else rules from data. We have also had learning plus probability. We have had courses here that talk about EM, active learning, I don't know, gradient descent, and so on and so forth. And then people started putting logic and probability together. So initially, probability theory by Nils Nielsen was introduced, which kind of probabilistic logic, which kind of viewed probabilities as putting constraints on logic space. And then it kind of grew to a big representation. I'll show you some of these representations. Okay? So the point is that we know that we can do learning, we can have rich representations, we can handle noise and uncertainty, and we have combinations of both. So obviously the one thing that we are doing is we are putting all three together, and that's what we call as statistical relational learning. Our representation is first order, we can do learning, effective learning, and our world is stochastic. We are not assuming that everything is noise free. We can handle noise and uncertainty. Okay? Students, whenever I give this talk, I make this point. When somebody gives a talk and has a cube, you can be almost sure that they always put their star at the top right hand of the cube. Okay? So always take it with a pinch of salt. Okay? Whenever somebody gives a talk, and so did I put this on the top right hand corner. I kind of adjusted the dimensions to make sure that we work. So before I talk about how we learn these models, I want to show about what it means to be relational. What is a relational model? Okay? So many of you know decision trees. So what I have here is a decision tree. What I'm interested in is predicting if a person, and that's the variable that is appearing in the parenthesis, is going to have a heart attack. Okay? So the first thing you're going to check is if the person is male. It's very well known in medical literature that men are more prone to heart attack, but heart attacks are far more lethal in women than they are in men. So men can survive multiple heart attacks. So let's say this is saying that the first thing is saying that if the person is a male, then you come down here. Now you're asking if the cholesterol level of this person, when the person is greater than 40, has ever been greater than 200. So it's like you're looking into this time, the temporal sequence of data, and you're cutting off at 40 years of age and saying after 40, has this person ever had a cholesterol of more than 200? Then the probability of a heart attack is 0.8. Okay? Most of you are under 40, but people who are over 40, all these are made up. So please don't get a heart attack by looking at these numbers. So the point is, the thing I want to really highlight is this is, you have the time sequence of a person, and this is, let's say, the age of a person. You're cutting it at the age of 40, and you're just searching to see if there is a cholesterol level that's greater than 200. Okay? In logic, it's extremely simple. You're just looking for, does there exist a measurement? Okay? Such a rich representation is really, really hard to do if you just take a flat feature vector, because you have to code every data somehow and project all of us into the same dimension. Okay? And then somehow aggregate all the columns beyond the age 40 and talk about it. But logic gives you this existential quantification for free. So you come down this path, which is false. This is false either because the person is under 40 or the cholesterol is never greater than 200. Remember, it's two conditions, so A and B. It can be false because of either of them being not satisfied, or both of them not satisfied. And then you come down here. Now you're looking at the father of the person to see if the father ever had diabetes. That's where relational comes in. Okay? Father of a person, of course, we all have one father, hopefully, at least biologically one father. But the thing is, this can be represented with friends. You can represent this with friends and talk about friends smoking. Okay? So, or friends who party too much, friends who eat in McDonald's too much. Okay? So this can be any relation, and that's rich. Again, this is basically saying, does there exist a person such that that person F is the father of the person that I'm talking about? If so, you're looking at the BMI of the person at the age of 55 to see if it's greater than 30. If so, the probability of heart attack is 0.77. So what I want to highlight is, I can talk in terms of existentials and attributes of a person. I can talk about relations and attributes of that relation. I can talk about specific values, like your standard machine learning algorithm can do. Is the value 50 at 55, is it greater than 30? Which is basically saying, is feature 21 greater than 30? Right? I could do that. So logic allows you to talk in terms of objects, in terms of relations of objects, and in terms of particular values of objects. So that's the power you get from logic. Okay? So this is a tree, and you have to kind of understand this tree to get the rest of the talk. Okay? So now I have three components where I'm first talking about how to learn these trees efficiently, and then I'm going to talk about how we can bring the human in the loop. And if time permits, I'm going to talk about a cool new direction that we are taking in this group. If time doesn't permit, Raksha will present this probably in spring. Okay? So any questions so far on representation before I move on? Yeah?
I have two short ones.
Okay.
The first one is, would you classify association rule mining as statistical relational learning?
Yes, I would say association rule modeling is one of the ways of doing statistical relational learning if you apply it on a relational database, right? Because I have seen people do that with flat data.
If I don't, I'm going to come up with exactly those types of rules that we're discussing here.
Right, but you need to have these
And also
father of friends, so friend of somebody who can do this. So association rule mining to me is a technique, right? I can get if I implement that on a relational database and that works with existentials, then yes. Select friends from this. If I can bring that query in, then yes. Yeah, and the second question?
I'll skip the second question. It was just about I think it's actually easy to encode these types of things if you're doing flat feature types.
Right, you lose the information. That is where the problem is. That is Jennifer Neville's thesis. So Jennifer Neville and David Jensen have shown that if you take an arbitrary database and construct a feature representation for that arbitrary database, you will lose linkage information and you will lose autocorrelation information. That's Jen's thesis. And so for most cases you don't, but you really have to sit down and carefully engineer your features. Here the feature engineering is minimal. You just take the data representation and you run your algorithm. So there you have to carefully construct the features. That is her thesis. That's the premise of her thesis. For instance, there is a paper by Perlish and Provost, and later by Foster Provost from NYU, where they show how these projections can be made from a database to a flat feature vector, and they're going one at a time to show that we can knock off this side, and so there is some theory on showing that not everything can be done, but when it can be done, you have to do it carefully. So not simple aggregators like count, max, min is not going to suffice. You need something like they have these multi-aggregations. You have to aggregate once and then aggregate once more on top of it. Then you can get something like this. So yeah, careful feature engineering, you should be able to do that, but that requires a lot of work, definitely. Any other question? Okay, so how are we going to learn it? Well, so when you think of graphical models and in general many of these probabilistic graphical models, there are three types of problems. The first one is where you don't have any learning, you just have reasoning. Okay, so somebody like the old classical AI expert systems gives you the model. All you do is when you have a test time, you have a query, you run your model and answer the query. Okay, there is no learning time. Expert is taking a lot of time to give you the query model. You have the model and then you answer the questions. The second part is where the expert gives you the graphical structure but doesn't give you the parameters. Okay, so if you have taken a probabilistic graphical models course, that's where EM comes in. That's where gradient descent comes in. Whatever your favorite optimization, that's where you solve it. Okay, so you could do that. That requires a little bit of data and the model. So both expert and the learning require more time, because expert has to design the model and then you have to fit gradient descent or EM or whatever, right? It can be non-convex if your data is hidden. So we know that. Then there is this problem of structured learning where you're only given the data, no model. And the goal was basically figuring out the model along with the parameters. Okay, so one of the questions that I asked my student Tushar when he started his PhD was if we can bring the structured learning somehow closer to parameter learning in terms of learning time. Basically, how can we make this efficient? Okay, to do that, what we are adopting is this notion of functional gradient boosting. This is really from the statistical side. Jerome Friedman from Stanford has this paper, really nice paper on gradient boosting. Gradient boosting is extremely simple. Let's say you have an initial model, which is a uniform distribution. You're saying with 0.5 probability something is true and 0.5 probability something is false. Okay, so that's the initial model. You make predictions on the data with this model. You take the difference between data and prediction. They become gradients. Okay, now I'll explain what these look like. What you do is for these gradients, you induce a tree. Now use these two trees together to make predictions, get the third tree, keep going until your final model is simply a sum of these trees. Okay, so how can you sum trees? First, the key change to the tree that I presented first was that in the leaves you had I had probabilities of a heart attack. But imagine removing those probabilities and putting a regression number in there. So anywhere between minus, let's say 1 and 1. Okay, what I can do is for every example I can run through the tree. If I guarantee that for every example you're going to get only one path of the tree satisfied, you're going to get one number from that tree. Okay, add those numbers, exponentiate it, normalize it, you get a probability. That's what we do. Okay, so that's how this is computed. The final probability is computed. Okay, so when I say data and predictions and compute the gradients, what I mean. So initially, let's say we will take a uniform distribution. So 0.5 of having a heart attack, not 0.5 of having a heart attack. So let's say according to the data, I have heart attack. Okay. So my probability according to the data should be 1, right? But my current model predicts it as 0.5. So my gradient would be 1 minus 0.5, which is 0.5. Okay. Dave is our lab's Hulk, and he looks too strong, so he's not going to get a heart attack. Okay. So his probability is going to be 0. But according to the current model, it says he has a 0.5 probability of having a heart attack. So his gradient is actually minus 0.5, 0 minus 0.5. The thing that you hopefully probably get now is all positive examples will have a gradient greater than or equal to 0. All negative examples will have a gradient less than or equal to 0. When I start at 0.5, 0.5, what am I doing effectively? I am pushing all positive examples towards 1, and I am pushing all negative examples towards 0. So each tree is going to try and push that much towards 1 or 0 respectively, depending on whether it's a positive or negative example. Okay? That's the high level 10,000 feet picture. Why is it validated? This is my, I think, maybe 1 or 2 math slides. This is one of my few math slides. So from Martha White's talk, this is going to be a relief if you're not a math person. If you're a really math person, this is the one thing that connects somehow to Martha's talk. That was a great talk, by the way. I really enjoyed it. So let's say I have a regression function where I'm just saying the probability of x being true given the parents from a Bayesian network perspective is simply a sigmoid function where you're just saying it's e power psi of something divided by e power psi plus you're assuming that negatives basically have a psi of 0. Okay, so it's 1 plus e power psi. If I have this, what do? Typically in graphical models, you will differentiate this. You'll write the log likelihood as simply the sum over all examples log of the probabilities, and then you will differentiate with respect to the probabilities. Okay, that's what you will do normally. We represent it by thetas. You differentiate it with respect to theta. What I am saying is in functional gradient, all we do is we differentiate it with respect to psi and not theta. Okay, why do you do it? Because if you differentiate it with respect to psi, Jerome Friedman showed that you can actually differentiate the likelihood of every example independent of other examples. So for every example, you can compute the gradient, which comes down to, well, according to the data, is the example true? If it is true, I becomes 1, minus the probability that your current model predicts the example to be true. Okay, so is the example true minus what is the probability of being true according to the current model. So you can compute these gradients. Okay, the theory goes like this. If you're interested, come and talk to me. The theory goes like this. If I take a gradient like this per example over the entire data set, this is approximating the gradient on the the log likelihood function. Okay, it's an approximation of the true gradient. The nice feature is the direction of the gradients will always be the same, which means if your true gradient reaches your maxima, this will also reach the maxima, even though it's an approximation. It's pretty cool theory, and so the final gradient is simply the sum of these different trees that you get. Okay, so that's how it's validated, and as I say, looking here, you can see that this is obviously a positive example. The other two are negative examples. Okay, so that's the theory. What can you apply this for? Well, you can apply this for many problems. What we have done is, first, anything that you're learning a conditional distribution, x given y, and y is the set of all features, you can learn via boosting. You're basically, from the set of all possible features, each tree gives you a subset of features. Putting all those features together, you're kind of doing a feature selection right there, and you're getting the small subset of features that you can work with. Okay, so once you can boost these conditional distributions, then obviously you can do what is called first dependency network, which is an approximation of a Bayesian network. The dependency network essentially says the joint distribution over a bunch of random variables is simply the product of the individual conditional distributions. Okay, this is okay, sorry, that's a mistake. This should be an approximately equal to. Okay, it's an approximation that works. And then you can actually boost Markov networks if you apply the pseudo likelihood assumption. If you have worked with Markov networks, you know that this is one of the oldest ways and probably the most popular way of training Markov networks. From Besag in 1975, she trained it this way, and from then on we've been doing it this way. You can learn policies like what Martha talked about and like what George Konidaris talked about. You can do imitation learning. You can learn from data the probability of choosing an action given a bunch of features. We actually have a really nice paper where we show much more theoretical properties of this algorithm using hidden data. And there, instead of maximizing the likelihood, we kind of maximize the lower bound of the likelihood, because that's enough to do the resampling. We have an EM version that we can do. We also have work on what if your data is not 1 and 0, it's probabilistic, so maybe it's like a crowdsourced data. You're asking, is this guy popular or not? And then you take that as a probability distribution, and you want to boost that probability distribution. Well, we have data that shows you can minimize scale divergence, and it's absolutely nearly the same expression. What is the true probability minus what is the predicted probability, okay? The other thing that we have done is we have handled multiple types of distributions. We can handle multinomial distributions. We have papers recently published in JMLR on Poisson distributions. Our recent AAAI paper can handle exponential distributions. So we've been trying to do this for multiple types of distributions as well. So that's the structure, and the cool thing is the results are really sometimes impressive. And yeah.
So where are the distributional assumptions taken that I didn't get? Like, are these some assumptions in the model?
So no, so the thing is that that's a very good question. The assumption was that till like last year, every variable that we are modeling is a multinomially distributed, and we were just trying to fit these multinomial distributions, which is your standard Bayesian network and Markov network. Recently we went and said, well, what if in your dependency network all the variables are Poisson? And then we were, so let's say you're predicting count of something, number of times somebody cites somebody, number of times somebody co-authors with somebody, and you're trying to learn a dependency between them given the entire citation data, and that's what we did using Poisson. And recently we have been doing this on exponential distributions, where we are trying to predict when an event happens instead of predicting if an event happened. Instead of predicting if somebody is going to have a heart attack, we are trying to predict when somebody would have a heart attack and fit a exponential distribution to that thing. And that paper is recently published. I have not yet put it on my webpage. So we make assumptions, yes, on the type of the random variables, and we can fit these different types of random. The assumption is on what you are learning, let's say, what you are learning. The excess. The assumption is really this P. What type of P are you learning? Is it a multinomial distribution? Is it a Poisson distribution or an exponential distribution? Sorry, I didn't clarify that, so thanks. So the results really look pretty impressive. This is our boosting, and this RPT is learning a single tree. MLN is the state-of-the-art Markov logic network. If you have ever heard Pedro give a talk, he would famously go out and say MLN is the cortex of AI. Okay, and kind of we beat the cortex. I don't know what to call us, but not just in terms of the performance measures, but look at the last column. We learned something in 9 seconds, which they took something like 36,000 times more than us. Okay, and this is in their data set. It's not our data set. It's their data set that we were able to beat them. We applied this on a multiple problems, movie recommendations, citations, learning from demonstration. Recently, we've been working with information extraction and a whole bunch of papers on these topics. Okay. Typically what I do is I kind of jump in and talk about two of the exciting topics, really the two projects that I think got me my job here, but I'm going to skip them. But I'll just say that we have applied this algorithm on several real problems. One is a cardiovascular study where we are trying to predict who's going to have a heart attack by looking at youth data. Okay, by looking at the data between 18 and 30, we were predicting if somebody is going to have a heart attack between 43 and 55. And our model performed the best. We have some really interesting observations. We applied this on a real electronic health record at Marshfield Clinic in Wisconsin, and ours had really at high recall regions the best performance. High recall regions is basically you don't want to miss anybody who has a heart attack by predicting they're not going to have a heart attack, and we had the best performance in that region. This is a nice AI magazine article that was published. And we also took this and applied on Alzheimer's prediction. We looked at three-way prediction of whether somebody is going to have Alzheimer's, is completely normal or is somewhere in between, by looking at their MRI data. We are looking at the MRI data as graph. Okay, so MRI images, we segmented it. Once we segment, we get a graph. Once we get a graph is a relational model. We apply our relational algorithm. Clearly, obviously, we got the best results. But the other cool thing was our top trees, the first 5 trees, had features that are regions of the brain that are the most valuable ones according to clinicians. And the other cool thing was we picked the frontal gyrus in our tree all the time. The first 2 trees always had frontal gyrus, and we were told by the neuroradiologists that we work with that is a matter of extreme debate inside the neuroradiology community. So I was even invited to give a plenary talk in their annual meeting based on this. So pretty cool results. But the key thing is all these are just learning from data. We are not doing anything more than data. We are saying data is gold, we learn with data, right? And by now, most of you should have figured it out that we could have easily overfitted anywhere here, because we are just pushing the error to 0, and then, yeah, sure, we got good results in everything, but is it because we were overfitting? Okay? So to do that, Philip and Shuo, they are looking at problems where your data may be noisy, but you have access to an expert. Can the expert provide more than what the data can tell you? Okay? Yeah.
Can you say a word or two more about cross-validation in a relational domain? How is that exactly done?
So,
That's another problem
right.
in any relational domain.
That's an excellent question.
Again,
Jennifer Neville does it. Lisa Gitur has her in her thesis. So in a relational domain, you see everything as what is called a mega example. So you're hoping that you will have these mega examples. So maybe there is one mega example of bioinformatics citations. There's one example of core AI citations. There's one example of HCI. There's one example. And then what you do is you kind of learn on 4 of these areas, apply it on the 5th area. And then that's how you can do the cross-validation. You cannot randomly subsample examples. You have to be very careful in figuring out. So think of it as multiple graphs, and then you're saying I'm going to train on n-1 graphs and test it on the nth graph. They are not disconnected, but hopefully you will pick the nth graph to be something that is mostly disconnected. Maybe there are like a couple of links that you can ignore and you can try and predict. But you're right. If the whole world is just connected by, everyone is connected to, what is it? Everyone is connected to each other by 3 hops right now. So you're hoping that 3 hops is enough for you to disconnect some part of the network. But that's a great question. Yeah, I don't think we have a solid theory on how to do cross-validation in relational domains. That's a great question. Yeah, we don't have an answer to that. So the point is humans can do more or less depending on how you see it. Okay? So the way I see it, humans can do more in terms of guiding the algorithm. Okay? So if I talk to a physician, he's got so much experience diagnosing people, giving them medicines. Why should I lose his experience and just mine his data? So that's why I say humans can do more. Humans can do less in terms of labeling the data. There's a lot of work to label the data, right? And any of you who works with NLP knows this already. We get a very small number of annotations and you have to work with it, right? The thing is, it's kind of paining me to see that SRL uses first order logic as underlying representation. And people who have seen first order logic for a long time know that expert systems were really built on first order logic systems, right? They were really classic AI systems. So my point is, if you can give advice, you have such a rich relation representation, why are you not using it? Okay? Even my research so far has been primarily data driven, or like Lisa Gitur's thesis, you have the entire model, all you do is reasoning, link prediction. I give you the probabilistic relation model, you do link prediction. Pedro does, I write the ML and you can do unsupervised semantic role labeling. Yeah, you can do that if you have the model. So what I'm trying to say is, on one side are examples, the other side are full models, and experts are kind of either believed to be mere labeler, who's just giving you the labels, and then you run your favorite big data algorithm, and you get the model out. Or they have, in some cases, as I explained, you have weight learning, EM, gradient descent, and so on. At the other end are where the experts are pure, all-knowing oracles. They are the be-all and end-all. You just use them for reasoning. This whole spectrum of region in between is completely left unexplored. That's where we are trying to come in. What if I had a little bit of examples and a small budget of the expert? Can I use both to learn something useful? Okay? It's not a new idea. It's been around again for 20 years. So for instance, there is so much work on knowledge-based support vector machines by Alvi Mangasarian, his student, and Jude Chavlik. Jude even gave invited talk in December 2013, I think, on knowledge-based systems. So we have knowledge-based SVMs from 2000 and 2001, knowledge-based artificial neural networks from actually 1994. Okay, that's when Jude and a student did the K-band work. And recently, Philip and us, we even did some work on inverse reinforcement learning. So we are inspired by this knowledge-based learning, where you have some knowledge that expert gives you and data that could be possibly noisy. And you can kind of build robust models using this data and the expert knowledge. Okay? So What are the types of advice that we can handle? The knowledge could be things like monotonicities. You can say as the feature value increases, probability of being a label increases. So you can say as the cholesterol level of a person increases, probability of heart attack can increase. Or you can say even synergistic statements. Increased cholesterol level will have a more adverse effect on people with high BMI than on people with low BMI. Okay? Low exercise can increase the risk of heart attack if you have high cholesterol than if you have low cholesterol. Okay? So things that basically talks about the qualitative relationship between some of the features and the data, that we call as monotonicities, essentially qualitative relationships. Precision recall trade-off. So most of the real world data is extremely imbalanced. Okay? Facebook friends. Okay? So I said somebody has 800 friends. Does anybody have 1,000 friends? Nobody? Even if you do, I'm pretty sure you're not going to put your hand up. But let's say you have 1,000 friends, and if you think you're popular, think a little bit. The population of India is 1 billion. You have 1,000 friends. So if I give you the population of India as your data set, you are a minuscule part of that. But that's the data we get all the time. That's where precision versus recall comes in. The expert could say, well, I don't care if you make me diagnose 4 more people for Ebola, but I don't want to miss one person with Ebola. Okay? You can qualitatively tell me how much importance you give for precision and recall. Our boosting algorithm can handle it. The third type of things that we recently presented is preferences. So you could say things like, well, I know that in the demonstrations I stopped at stop sign only 50% of the times, but I prefer that you stop at all stop signs. If it's safe to stop, stop at a stop sign. Okay? That becomes a preference. You could say things like, I really think if some 2 people have co-authored at least 10 papers, and if one is a professor and other is a student, I prefer to call that student. I prefer to call the advisor, the professor as an advisor of the student. Okay? So you can have these preference statements. If you want to preference elicitation in classic AI, Craig Boutillier has published a lot of papers on this. And we have done this on POM-DPs. We have done this on Bayesian networks. Now we are doing this for probabilistic relational models. Philip paper can actually handle this. Okay? So we have also looked at multiple problems. We can do this in relational classifications. So you can have things like membranes can have many neighbors. And then you can identify membranes using this one piece of information. Things like in imitation learning, slow down for red lights. We also applied in transfer learning, for instance, where you can drive a car on a straight road, and then when it comes to a curved road, you can't just take the policy and directly apply it. You want to say, well, you need to be a little slower here, because this is a straight road and this is a curved road. You need to slow down when you approach a curve. Okay? And then we can apply it on transfer learning. Okay? So the way we give these advice really are trees, or actually Horn classes. We convert everything into a first order logic Horn class, and advice is a Horn class, and you take this advice and you can apply it. So one way of applying advice is to treat it as an initial model and let the data kind of take it from there. But the problem here is, because the algorithm overfits to the data, if your data is noisy, it kind of overrules the expert advice. So expert advice becomes useless after some time. Okay? So you will kind of correct the advice with wrong data. You will overfit to the data, but not to the advice. Okay? So this is the example that Philip came up with. If this is the ground truth, let's say this tree generates the ground truth, this tree generates the training data, you can see that almost all the parts have similar weights except the last one where you have a systematic noise. And then you use this as initial model and then learn from this. This is my advice, which basically gives some advice. Then what happens is the data can kind of overrule, and this tree is very close to the training data than it is to either of these two. Okay? The point being, if you don't get this example, simply assume that the algorithm will overfit to the data, not to the expert. So the expert kind of gets written off. So what we did was we actually said, well, don't keep it outside. Instead, bring it inside the optimization function, where you have an advice effect and the data effect. Compute this separately and this separately, and then compute the gradient, and so on. Okay? So there's a couple of papers that we have published on this, and the idea is your earlier equation that we looked at simply had these two terms, basically this divided by exponential of this plus 1. But now we are adding a cost term to it. The cost is how much you violate the expert advice. So it's a very simple thing. If you are in preference case, this is the number of times your data supports the advice minus the number of times the data violates the advice. So your gradient comes out nicely to be, this is my previous I minus p expression plus some lambda times how many times do you satisfy the advice minus how many times kind of you violate the advice at a high level. Okay, so that's what we have been doing, and so you can quickly see this explicitly trades off between what the data is saying and what the advice is saying. And this is where we can even handle the cases where advice is wrong but data is correct. This kind of takes care of that. Okay, so I'm just giving you a sample result where we applied this on a graph segmentation problem. Really this is Philip's work, and with advice we got nearly close to 100% accuracy, but if you don't use advice and just our boosting algorithm we had 70% accuracy, and then using advice as initial model kind of did okay but still not good enough. Okay, but using advice into the algorithm made it better. So we did this again with cost sensitive learning where we talked about precision versus recall. These are the two, the last two are the precision versus recall. The red curve here is really the functional gradient boosting. These are the other ML and single tree methods. And as you can quickly see, our methods are doing really better compared to even the normal boosting if you have class imbalance data and if you can provide some advice on precision versus recall and so on and so forth. Okay, any questions on this before I really rush through the last part in 5 minutes?
Choice of lambda.
Right, choice of lambda, cross validation.
See, I mean, there's always some parameters that bother me, right?
Right.
Because you just introduced another parameter and you're hoping
That
let's try to give you a hard time. That parameter will have a value that will outperform others, right?
Right.
So how does that happen now?
Right, so that's a really good question, right? So if you have a lot of good data and some noisy data, then lambda setting it to any reasonable value is okay, right? If you have a lot of noisy data, then lambda has to be high because it has to rely on the expert. So it's something that we have been kind of setting with intuition. But when it comes to precision recall, actually we have a lot of results on this paper where we show as long as your alphas and betas are within a certain range and you don't have to choose them carefully, you will get the right model. Their performances were never different. This is just a truncated this thing. I don't want to show all the alpha beta. The paper has them. So in general, the learning algorithm is robust to that parameter selection within a certain range. You can't unreasonably say, well, I'm going to keep a low lambda, but my data is really noisy. Then you're not going to do well. So the lambda is between 0 and 1, and we tend to keep it 0.5 for all our experiments. Is it? Roughly. Yeah, somewhere between 0.25 and 0.75, we were getting robust results if your data is reasonably good and you're wrong only at certain instances. So if I'm taking a drunk college student's trajectory on learning how to drive, I need a good lambda, right? But if I'm learning a more responsible adult driving and you're looking at it, the lambda can be even lower. It's okay because most of the time the adult is going to do fine. So that's the idea. But thankfully they are not as sensitive to these parameters as the other methods are, definitely. But yeah, I'm not sweeping anything under the rug. Yes, it is an issue. Yeah, we have to do this. Great question. Anything else?
What if the advice is subjective? So
Excellent question. What is the advice is subjective, right? And more importantly, you can ask the question, what if the expert is good in one part of the area, right? So maybe somebody can give you good advice about MRI images, but somebody else can give you good advice about electronic health records. Somebody else can give good advice about the genetic sequences and so on. So we are looking into that problem next, where the current assumption is the expert kind of knows the problem fully. The next assumption is what if you have experts, the next problem is what if you have experts who are particular experts in areas, which is kind of like subjective, right? Within that area, that expert is really the expert. But his opinion on or her opinion on the other areas are going to be subjective, and you want to take it with a pinch of salt and figure out how to learn. That's really the next problem that we are doing. But excellent question. Currently, we are assuming that the expert kind of knows the domain very well, all the parts of the domain very well. Unreasonable in many places, but this is the first step. So hopefully, we'll get there.
and if we're coming from some knowledge repository.
Right, it could be coming from some knowledge repository. So we are trying to, for instance, Raksha has been working on trying to learn this from NEL. NEL is this never-ending language learner. We are working with Tom Mitchell on this. So can we get some knowledge from them, figure out what NEL learns, use that as a knowledge to learn on some regions that we have not learned next. So, but yeah, that's a great question. Yeah.
You haven't incorporated actually having a cost to query your expert,
right? Right. That is what he is doing currently under the framework of active advice seeking, where you have a budget, and within a budget you basically can ask questions, and within that budget you can think of like, okay, I'm allowed to ask 10 questions. What is the most 10 valuable questions that you can ask? And the assumption there is basically saying here the expert has to give you everything, and the expert really doesn't know how the learning algorithm works. But if the learning algorithm itself asks the question, then it knows what it needs because it knows where it is uncertain. That is Philip's current thesis. He's trying to do this active advice seeking, where he's basically saying, given a fixed budget, can I ask these questions to get the answer? It's a great point, yes. Any other questions? Okay, so I'll wrap this up in like 3 minutes, sorry Raksha. So we are looking, we are inspired by this. We are basically looking at asking the question, can I do transfer learning across domains, right? So if you look at transfer learning, most people, including us, this is what we did. We learned in a real-time strategy game how to defend 2 towers from enemies. Now, and then we applied it on 3 towers. Okay, that's what transfer learning mostly does. But what we are looking at are domains that could be completely different. Okay, as an example, this is what Raksha was able to learn from NEL data. So in NEL, which is Tom Mitchell's never-ending language learner, you have a lot of knowledge about sports. Okay, and the sports, the knowledge could be that if 2 teams are members of the same league and one of the team plays one sport, then possibly the other team plays the same sport. Okay, what we can do is we can take rules like this that are learned in one domain and apply in another domain to say something like, if 2 companies are in the same economic sector and if somebody has a share in one company, then the person possibly has shares in the other company. Okay, how much this is true could be very different, and I don't care about it. The fact is I can induce a rule like this by just looking at a rule like this. Okay, so what we did was, and these rules are not present in NEL. These rules are present in NEL. So we were able to augment their learner with new rules that we were able to learn from data. And these are probabilistic. All these are probabilistic rules. They are not yes, no. They have a certain probability of being true. Okay, so what we did was we basically looked at the bias, kind of the language bias from the source to the target. I'm going to skip everything. I'm just going to tell you how we did this. So let's say in source you have something like you're interested in predicting if the purple P is advised by the red P. Okay, the red P is the professor, and then the professor writes a publication which has the student, then the student is advised by a professor. Basically, if the student and the professor co-author the same publication, then the student is advised by a professor. Not always true, but it's a good rule, right? I can do this, take the same thing, figure out how this search could have happened, and do a similar search in the target domain, and I can say a person works under the other person. If they both work in the same movie, one of them is a director, the other is an actor, then the actor works under the director. Or if they work in the same genre and one of them is an actor, then the actor works under the director. Okay, so the point is, how do we get this? We are just figuring out how we are walking in this domain. So think of it as a random walk on the source domain, figuring out how you can get all possible random walks like that in the target domain, and then we get the expert in. We present these rules, or some of the best rules, and ask the expert, can you refine them for us? Okay, and very good results. This is a work that's been at ICDM this year. She presented it last week, and we are extending this to bring in the expert. She built a tool where we can actually have a tool. The expert could interact with the tool and say, well, this path doesn't make sense. This path makes sense, or this path can be removed. And we are trying to figure out if this can be reducing the burden on the human. Okay. Anyway, so apart from this is a shameless advertisement for my lab. We actually work on a bunch of other problems, more on the fundamental research. We actually even do parameter learning, piecewise learning. We are extremely interested in probabilistic inference. If some of you remember He Vandenbroek, who even interviewed here for a faculty position last year, we work pretty close with him on problems like belief propagation, inference, dynamic inference, and approximate counting. We also do a little bit of decision theory, imitation learning, IRL, POM-DPs, and mainly UAI type methods. So conclusion, hopefully I kind of convinced you that we have a powerful learning technique for statistical relational learning where we are learning a large number of small rules, and we have been applying this on real applications. We are trying to get seamlessly human advice integrated into this learning framework. Sorry, I didn't have enough time to talk about the transfer, but the transfer is really built on inductive logic programming search techniques. So if you're interested, Raksha can share the paper. So we've been trying to focus on more applications. NEL is one. We have been funded on NLP to do these kind of learning relation extractions. As answer to your question, we are really working on actively procuring advice. Like what you said, we could have multiple experts in multiple problems. Can we get advice from each of them and use them? I'm also really interested in temporal modeling, not just static predictions when an event occurs. I think that's something really important for us. And other types of distributions, as I mentioned. There's also people like Mayuk who have been working on approximate counting. So most of these SRL models really hard to count, and counting is an extremely important process. How can we approximate it via some graph theoretic methods? So we even recently submitted a paper with Melanie who on figuring out how to do this approximate counting. So this is an old list of collaborators. So thanks to all my collaborators who have been extremely helpful. That's it. Thanks. Yeah.
I have one general question maybe about the general SRL framework. Is there something equivalent, for example, in general machine learning, there is theory that says you can learn a posterior distribution if you have enough data, learn in a particular way, a powerful model, you will be fine. That's what the theory says, right? Is there an equivalent theory here that
in learnability?
The same thing on the relational domain in some way?
Yeah. So under some restricted assumptions, if you assume the use of only Horn classes, the assumption of Herbrand universe, which is basically finite, countably finite domains, really large countably finite domains, then we can have theories that are similar to that of the propositional case. Manfred Jaeger and a couple of others have written papers on that. So there is some theory on this, but the general case, well, first order logic resolution is not easy. So same thing here. Probabilistic reasoning is not easy, NP hard, right? Probabilistic inference is hash P complete. So this is, if at all, at least hash P complete. So the general problem is hard, but if you have these specific restrictions, Horn classes is one, and we restrict the size of the domain, then we have some learnability results that exist. Wonderful question. Anything else? Okay, thanks.